Welcome to week 3 of regression, and what we're going to cover this week is the series of assumptions that underlie multiple regression, and usually specifically ordinary least squares. So your standard multiple regression that comes in most statistical packages. So the first thing is I have to defend why we should even go over assumptions, since you learn that early on that most of what we do in statistics violates the assumptions, and that we shouldn't really pay a whole lot of attention to them, but there's a reason why we should. And the first, probably the most important reason, is that we need to conclude from our regression models that our estimates are blue. And blue means best linear unbiased estimates. And why is that? Well, remember, the purpose of regression is to describe and then eventually to predict. And we want to be able to describe our data and then be able to predict future values given variables that we have available to us. And if we come up with terrible prediction equations, then our predictions will not be terribly useful. So what we want to do is we want to meet the assumptions for reasons that allow us to have these best linear unbiased estimates. So what I want to do is I want to give you a very quick example and show you what this blue thing is all about, and how you can determine whether your model suits the best linear unbiased estimates given the assumptions. So first, without any hesitation, the first thing I want to do is I want to create a population. So I'm just going to create two variables, x and y, from a population of 100,000. And you can see here the relationship should be there's two parts error to one part signal for x. So they should share about a third of the common variance, and so your r squared should be about 0.33 or so. And what I did was then I ran a linear model, and I can do a summary of lm3.p, which I haven't done before. So let's see, how did we do? Yeah, about a third of the variance is shared. So that's good. Okay. Now, this is a population. Rarely, if ever, do we do anything in populations. We sample. So what I want to do is I want to run through a very simple, oh, I got some code here that I can kill. I want to run through a very simple bootstrap model, and the reason why I want to run a bootstrap model is the bootstrap model enables us to resample the data so that you can see how a series of resamples will stack up for giving us the best linear unbiased estimate. And then we can compare one single sample so that you can see what happens with a single sample and how it stacks up with the true population estimate, as well as to the estimated bootstrap sample. So I created this little function, and I want to show you what it all comes down to. I've run these models already, so let me just run this first one. So I'm running all the models again, and then I want to show you what the histogram looks like and what that function produces. So the function produces this histogram, and I just labeled it my histogram. And the histogram, there's quite an interesting set of lines here. So underneath this black line is a red line, and that red line is the mean bootstrap sample, and this is for the intercept. So the intercept is about 0, which makes sense because x and y are both standardized. And the black line is the population parameter for the intercept for A, given my 100,000 sample. Now what I've done here is I've sampled 100 observations, that's here, 10,000 times from my population of 100,000. So I have 10,000 now resampled intercepts and slopes from these simple bivariate regressions, and each one of these is produced by a sample of 100. And why 100? I just chose it arbitrarily. And the distribution that we've created are all the parameters, and this is just for the intercept. So we know that the population value for the intercept is 0, and this blue line right here is our estimate from one single sample taken at random from the sample. And what we want to be able to say is that this regression parameter, in this case A, is an unbiased estimate. So it can fall anywhere in here, and it is the best linear estimate. So it is the best linear unbiased estimate. A biased one would mean that it systematically falls on one side, and best, if it were not the best, what it would do is it would fall outside this range and would not be a good approximate value or approximate estimation of our population parameter. Our population parameter here is shown by this black line. So remember, in statistics, we always take samples, and those samples are supposed to give us a clue about what the population would be. And the reason why we want that is, well, one, we don't have access to the population. So we want to be able to generate some prediction based upon observed values. And the better we can do that, the better our predictions are. Now, we can only produce good prediction models if we adhere to the assumptions that I'm going to go through in all of the subsequent videos. So this first video is just a demonstration of why those assumptions are so important. I'm going to run through, this is what the histogram looks like for the B value. And for the B value, you can see, so for the intercept, it was right next to and slightly below the population parameter. Here, our B is slightly above it, but well within the range of, this is 2 standard errors, well within range of 2 standard errors of the population parameter. So we're looking pretty good. And if I resampled this many times, if I took a new sample of 100 or 200, this blue line would change, and it wouldn't be systematically off to one side. Now, it wouldn't if our assumptions are met. If we fail to meet the assumptions, then the parameter estimates from our sample will always fall on one line, or one side of this line. And so therefore, it won't be unbiased, or it will be biased. And so we want to be able to understand what these regression assumptions are so we can avoid having biased estimates in our regression parameters. So stay tuned. We're going to go over all the rest of the assumptions. I'll probably handle one assumption at a time per video.